I was just had a little trouble communicating over the weekend, so with emails, and it's really hard when you ask me a question in email and then I respond, and then we start getting emails across and stuff like that. So it was just I just want to make it. Huh? No. I'll let you in on a little secret. That's not recording. Is that recording?
Yeah.
Oh, it's fine. I'll let you on another secret. It probably won't be until next Monday. It's unfortunate, but it probably won't. No, it's the fact that I was left my glasses at a place that doesn't even open until tomorrow. It doesn't open again. I'll have to be here on Saturday. It's not open until tomorrow. I can't really see. I was completely off topic. When you make your YouTube video for a flag, this is Dr. Collins going off on his little tangents here. I was in a play once, the church production, and they had to put stage makeup on me. Oh, it took them hours to just get like the eyeliner on me so that I wouldn't get washed out. I was like, this? I'm not putting contacts in my eye. No. All right, let's go over here. Questions? Chapter 30, what's going on? Oh, don't all jump at once.
You just jumped in. No, I forgot which one it was.
Huh?
You just clicked on
The very last one? All right, 30.5. Okay, an inductor has a current. I of t is equal to 0.580 amps times the cosine of 275 seconds inverse times t flowing through it. If the maximum EMF across the inductor is equal to 0.460 volts, what is the self-inductance of the inductor? Okay, you have an inductor. Don't know what the inductance is. We know that the current going through it as a function of time is equal to 0.580 amps times the cosine of 275 seconds inverse times t. Now, when I write this down in terms of the number inside of here, that seconds inverse may be misleading because when you, out of context, it would be misleading because it could be radians per second or it could also mean hertz. In this case, which is it?
What would you restate the thing?
The 275 has a unit that's given in the text as seconds to the -1, inverse seconds. Depending on what context that is, it could either be radians per second or hertz. If I tell you what it is, if I said this is the frequency is 275 seconds inverse, then you know that it's hertz. If I said that's the frequency. What about inside of a cosine?
Radians.
That would be radians per second inside of a cosine. Okay? They're not explicit about that, and a lot of times I guess they won't be. Okay? But just understand, if something's inside of a cosine multiplied by t, this number is in radians per second. Because if I take cosine of just a number, that number has to be in radians. Yes?
Is the final going to be these chapters? Or I think I already asked you about it.
You asked, let's talk about the final now. We're working on chapter 30. Okay, fine. The final will be based off the last couple chapters, and there's also a comprehensive part. Okay? We'll go over that and get closer to it. We're not there yet. All right, since this, I know, but I'm right in the middle of a problem. And you'll get me distracted. Okay, so I was thinking. All right, so So then it says if the maximum EMF across the inductor is 0.46 volts, so I know what this is. You can write Vmax, but at least in this case I prefer to write the Emax across an inductor. So we're given that this is 0.460 volts. And then we're asked, what is the self-inductance? What is the self-inductance? All right. So we go back to what is the voltage drop across an inductor? Voltage drop across an inductor is what?
Negative L, d I d t.
Let's just say L. Let's just use the absolute value here times the IDT. Okay, so what we have to do then is take the IDT. Find a derivative here. Okay? So if we take the derivative of this thing, constant, it's just that constant, 0.58. Derivative of cosine is negative sine. I'll put the negative over here. So I got the sine of 275t. And then I take the derivative of what's inside, which is 275. So we put that out here. Somebody multiply these two numbers together. Tell me what you get. I'll say 160. So 160 sine of 275.
When we do the sine, what unit comes out of that sine?
What unit comes out of here?
It's just the sine part, since it's radians over seconds.
Well, once you no longer talk about an angle, that the radian doesn't matter. Because the radian, remember, is a unitless number. And the only reason why we use it is because we're talking about an angle. The only distinction I need to make is between that and a frequency f, which is defined as being cycles per second. Okay? So in other words, there's a 1 over seconds that comes out of this. So this 160 has units of amps per second. That's the units of 160. Okay?
And what comes out of the sine is just a second.
Just the 1 over seconds, yes, comes out of it. All right, so what's the maximum of this? 160. Okay? This plus or minus doesn't really matter in terms of the maximum, because then I can just say, well, sine is -1, then that makes a maximum of 160. Okay? So if you're just looking at the maximum, this negative sign will come into play a bit later. We will talk about how the negative sign comes into play, okay? Where you get a negative or positive. Not yet, we're not there yet. We're just looking at the maximum here. So the maximum dIdt is that. So in other words, the maximum voltage across that inductor is equal to the inductance multiplied by the maximum dIdt. I mean, I didn't give you this formula, but you can reason this formula through. In other words, you don't need me to give you that formula. Okay? Just something you need to reason. This is maximum when that derivative is maximum, because the inductance itself is a constant. The inductance itself, just like a resistance of a resistor or the capacitance of a capacitor, is a constant. It depends on the geometry and the makeup of the circuit element itself, the inductor itself. Plug in numbers. 0.460 volts is equal to inductance multiplied by 160 amps per second. So what's the inductance here? people. All right. Guys in the back to your rows. I want to hear from you. One of you at least get out your calculator and start calculating 0.460 divided by 160 and tell me what you get. Yeah, you had a question. No, you're not in the back 2 rows. I'm forcing them to do it. But thank you for calculating. You can tell me if they're right. What'd you get?
2.875.
2.875.
10 to the negative 3.
Okay, 2.875. 2.86 times 10 to the negative 3. And we get a weird unit of volt seconds per ampere. I don't expect you to be able to translate volt seconds per ampere. Okay? What's the units of inductance? Henry. Says Henry. Okay? And then the milli here would just mean it's millihenries. And so your numbers, I don't know, do the numbers vary on this thing? Do your numbers vary?
Yeah.
Okay, good. So then I can do this. Because notice that my numbers, for some reason, I guess maybe rounding or whatever it is, I got 2.86. You know, we got 2.86. Oh, he did say 875? Did you say 2.875?
Yeah.
Oh, okay. See? Oh, okay. Well, fine. I don't have to round. Okay. There it is. So you just click the number and you get it. Okay. What they're going to give you is give you choices with common mistakes, I suppose. Like if you don't take a derivative, or well, actually, if you don't take a derivative, you're off by a factor of 160. So. All right. How about another one of these? How about another one of these?
7.
Number 7, which is which one? 1, 2, 3, 4, 5, 6, 7. 30, 34. An 18 microfarad capacitor is placed across a 22.5 volt battery for a few seconds, and then is connected across a 12.0 millihenry inductor that has no appreciable resistance. After connecting the capacitor and inductor together, find the maximum current in the circuit. That means there's no resistance in your circuit. In other words, we're creating an ideal LC circuit. It's ideal. Okay? So, 18 microfarad capacitor is placed across a 22.5 volt battery for a few seconds. Okay, so we put this. Go ahead and draw this out. This and this. Okay. This is 18.0 microfarads, and this is a 22.5 volt battery. Okay. Now, why would they say for a few seconds? To allow the charge to build up. Okay? In this case, it wouldn't take very long at all. Okay? Because if you don't use any kind of resistance here at all, the resistance of these little wires is comparable to about 0.1, maybe 0.01 ohms. Very little resistance in switch wires and things like that. Very little. In fact, those might even be wrong. Check it out. And you got an 18 microfarad capacitor, so your time constant is going to be on the order of some nanoseconds. So leaving it for a few seconds is plenty of time to get the thing charged. Essentially, if you don't put any kind of resistance in a circuit like this, you pretty much just charge it up. Okay, you just charge it, and all they're telling you is it's charged to 22.5 volts. Charged to 22.5 volts. Okay. Oh, so what can we figure out from this already before we even go on to the other part of the problem? What could you hopefully figure out from this information without even going on to the other part of the problem? Q. How much charge I've got on my capacitor. Okay, so how much charge do I have on it? Let's see. Okay, Q equals, where'd it go? Well, let's remember the voltage across capacitor is what? Q over C. Let's go these three. VR. Better know this one. See? IR. Okay? Just remember, I'll get angry if you don't remember this one. Okay. Yeah. This is our new one, LDIDT. Okay, so Q here is CV. Okay, so I just take 22.5, multiply by 18 microfarads. And for the moment, I'll go ahead and leave this in microcoulombs.
$405.
405. Take 405 microcoulombs. Okay, now there's a couple of ways we can do this. There are a couple of ways we can do this. Let's see if both of them give us the same answer. Let's see if both of them give us the same answer. Okay? The first thing is to go to an our LC circuit, because now what we do is we take the 18.0 microfarad capacitor, hook it up to a completely ideal inductor. Completely ideal inductor, and that inductor is 12 millihenries. And we are asked, what is the maximum current in the circuit? What's the maximum current in this circuit? We disconnect the battery before we do this, by the way. Just. All right, so one way to do it is to use the equation for charge as a function of time. Charge as a function of time. So we got Q is equal to Q naught multiplied by, whoops, cosine of omega t. That's the form of it. Sorry, I almost put sine there. It's cosine. I know because it started out with maximum charge, so I need that to be cosine. Start from the max charge. Okay, where my omega is given by 1 over the square root of L times C. So we can solve for this, okay? So 1 over the square root of 18 times 10 to the negative 6 multiplied by 12 times 10 to the negative 3. Somebody please calculate this. Tell me what you get. Just believe me, I don't know. No chance of doing that in my head. Yeah, give me the one over. Give me the whole thing.
2151.666.
2151. So, do I have a confirmation on 2152?
Yeah.
Okay, 2152. All right, so we've got 2152. This, by the way, is radians per second. I'll go ahead and write radians per second. Okay, so then what we can do is we can go up here and we say, okay, so the current in the circuit then is equal to dq dt, which is equal to Q naught times negative sine omega t, and a factor of omega comes out here. So the maximum current that you get out of this is Q naught times omega. Q naught we found is 405 microcoulombs. So we want to convert this because we're going to multiply by this nice big number here, and maybe we'll get something that's, so 405 times 10 to the negative 6. Multiplied by my 2152. .87156. fruits of that.
Cool, for a second. Damn.
Okay, let's go check on the, let's go check over here on masculine physics and see if, yes, indeed, the numbers are correct. So 0.81, no, 8717156. Oh, no. 87156. It'll say your significant figures are, you just put way too many together. All right, let's see. When the current is maximum, what is the charge on the capacitor? You might want to tell her she's on YouTube now. All right, so when the current is maximum, what's the charge on the capacitor? 0, because when you have maximum current in the inductor, there is no charge on the capacitor. So this is 0. How long after connecting the capacitor and inductor together does it take for the capacitor to be completely discharged for the first time? Tricky, but let's find out. Let's take a look. Okay, so you want to remember the cycle that it goes through, okay? So we start out here. Plus, minus, I'll go ahead and put plus positive on that plate, okay? Then this is 0 with current going to the left. Then we go back to this situation here, where we have a plus no current. Then we go to where we discharge the capacitor again. We have current going the other way. And then we go back to the beginning, okay? So how long does it take for each of these steps? Well, remember, this is a cyclical pattern here, right? So we have 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Each one of these are equally timed. There's no difference here. So each one of these steps is equally timed. It's just like a pendulum. You know, if you have a pendulum, swings one way, okay? 1, 2, 3, 4. 1, 2, 3, 4. Each parts of the swing are going to be equally timed, like this. All right. So each one of these steps, here's where it's discharged for the first time. This is 1/4 of the period of the system. That's 1/4 of the period of the system. We can calculate the period. We can calculate how long this takes to happen, right? Because we know the relationship, or you've seen the relationship, or I'm going to give you the relationship. We're going to have an interesting YouTube video. Is 2 pi divided by omega. Okay? 2 pi divided by omega. So let's do that. So the period here is 2 pi divided by my 2152. So what am I going to get for my period here?
2.96 times 10 to the negative 3.
Now, is that the answer we put in? No. What do we have to do with this?
Divide by 4.
Divide by 4. So now divide by 4. Times 10 to the negative 3. So it's don't think this thing will take it because, you know, let me go and put this in. So this should be, I could either like times it all out, but I'll just say 0.74, and where do I put the X? I put this thing like that. 10 to the, where'd it go? Where are you? Oh, there it is. -3. All right, now it's telling me my sequence. Then it says, how long after connecting the capacitor does the inductor together does it take for the capacitor to be completely discharged for a second time?
Can you just multiply that?
No, same amount of time.
It says,
Well, let's see. So, so when it's completely discharged the first time is this, 1/4, so 1/4, 2/4, 3/4, there it is. So it's 3/4 of the period, it'll be discharged again. Just multiply that by 3. How about another one of these? Anybody want another one? Are these too easy or something?
Pretty sure I put in the exact same number.
Yes, which one?
Both.
Scroll down. $19, this one here. That one. Circuit is shown in the figure. This one. Looks like fun. Lots of fun. All right, let's do this. For the circuit shown in the figure, the inductors have no appreciable resistance, and the switch has been open for a very long time. Okay? Which means that all the inductors have dissipated all of their current. Fine. So then it says, the instant after closing the switch, what is the current through the 60 ohm resistor? Okay. All right, so let me redraw this. So now we got 100 volts. And switch.
no, like switch
Huh?
over to.
Oh, I'm just drawing this, and you can look at that diagram and draw it probably better than than looking at me draw it. You don't need to see me draw.
I was just
Fine. Fine. And then we have a 10 ohm resistor. Oh, look at that great sawtooth I drew. Amazing sawtooth. Best sawtooth. Oh, look at that. Okay, so we got down like this. Right there. Oh, there's that 60 ohm resistor we've been asking about. There it is, 60 ohm resistor. And then the 30 ohm resistor over here. So we got 30 ohm resistor here. Over on this side, here we go. Over here. There we are, and then we have a 15 milliamp inductor here. Over here we have a 40 milliamp inductor. And here's our 60 ohm resistance, and here's a 10 ohm resistor. All right. So, now immediately after the switch is closed, find the current through the 60 ohm resistor. All right, so immediately after the switch is closed, what do inductors do?
Block.
They block current. So no current can flow through the 40 millihenry inductor here. No current can flow through the 15 millihenry inductor. No current will flow through these two. Okay? So let's see. Well, there has to be some, not no current because I got a path here. So I go through the 10 and I go through the 60. 60 ohm resistors, those will allow current to flow. There they are. Ta-da. Okay? So 10, 60. That's how many ohms are we?
70.
Yeah, those are in series because the 10 ohm resistor is actually in series with everything else. Okay? So it's in series with all this stuff, but the only thing out of this is an infinite resistor at t equals 0. That's an infinite resistor at t equals 0. You got 60 ohms there. So if I took 1 over infinity plus 1 over 60 plus 1 over infinity, that would equal 1 over 60 because 1 over infinities are 0. Inverse that, so these three in parallel immediately after it starts off 60 ohms. That was the second explanation if you didn't understand the fact that no current's going to flow through here, so it all has to go through the 60. Okay? So any current in this circuit goes through the 60 ohm resistor, so therefore it's the current in the 60 is the current for the circuit. There's only one path. It's just 100 volts divided by what? 70 ohms. That's it. That's it. Okay. What is it?
1.43.
Okay. So this is immediately after. Let's do this one too. Does it actually? Oh, it does. Oh, it asks you more. Oh, wow, there are more questions here. Okay, that's fine. I thought it was just A here. Okay. So, the instant after closing the switch, what is the potential difference across the 15 millihenry inductor? Okay. So, we're still immediately here. Okay. Said, what is the potential difference across the 15 millihenry inductor? So we want to know what is the voltage across the 15 millihenry inductor. I'll write 15, okay, for 15 millihenry inductor, immediately after the switch is closed. Well, let's see. All right. First of all, this part of the circuit that the 15 millihenry inductor is on, this part of the circuit right here, 30 ohm resistor and the 15 millihenry inductor, it's directly parallel with what other circuit element?
60.
The 60 ohm resistor. Also, by the way, the 40 millihenry inductor, but we don't know anything about it yet. Okay? So we just know that these two are directly parallel with that 60 ohm resistor. So no matter what, the voltage drop across this 60 ohm resistor will always be the same as the sum of the two voltage drops here. They're in parallel. It has to be. We still can't forget that. I mean, all this fancy stuff of blocking current and everything else. And by the way, the voltage drop across the 40 millihenry inductor is also got to be the same as the voltage drop across the 60 ohm resistor and the sum of the voltage drops across the 30 and this. They're all in parallel. Parallel equal voltage. Parallel equal voltage. Okay, so now what we can do is we can take this thing and say, well, I know that the voltage across the 15, the voltage across the 60 ohm resistor, so let's go ahead and write that down, is equal to the current through it, which is, what is it? .43 amps multiplied by 60 ohms. So what's the voltage across the resistor? It's not quite 100. 85?
85.8.
Okay. Let's just say 86. They'll yell at me for not rounding off, but yeah, I guess. Okay. All right, so now we want to find out what this voltage across the 15 millihenry inductor is. And what we know is that the voltage across the 15 millihenry inductor plus the voltage across the 30 ohm resistor, just to remind myself what I'm talking about here, okay, has to equal this voltage here, which is equal to 86 volts. Okay, so now let's take a look at our immediately after thing. Immediately after thing. Okay? So immediately after the switch is closed, if I look at this branch here, how much current is flowing through it? 0. What does that mean about the voltage drops here? There's no current flowing through it. No voltage drop across the resistor, not the inductor, because the voltage drop across the resistor is 0. The voltage drop across the inductor, remember, doesn't depend on the current. It depends on the change in current. The change in current with respect to time. So the voltage across the resistor is 0 because there's no current. So the voltage across that 15 millihenry inductor is equal to 80 volts. In fact, we could do a calculation and say, how fast is the current changing through the 15 millihenry inductor immediately after the switch is closed? So if we can calculate this immediately after, because I know that the voltage drop across this has to equal the inductance multiplied by di dt. The inductance is 15 millihenries. That's equal to 86 volts. So therefore, immediately after the switch is closed, wow, that's a pretty big number, isn't it? You get it. I'll let you do it. Nobody seems to be jumping on it. So remember, inductors' voltages depend on the change in the current. Okay, change in the current. Okay, the last part of the problem asked, after the switch has been closed for a long time, what is the potential drop across the 60 ohm resistor? Oh, this one here?
Yeah.
All right, so now a long time after the switch is closed. A long time after the switch is closed, okay?
Is that bottom part C?
No, that bottom part's not C. That bottom part's something I made up. I made up to explain why you're looking at the voltage, the difference between looking at a voltage drop across an inductor and a resistor. Okay?
And to do that, you took the voltage that you knew and you found.
Right, this voltage is was 86, right, and then I could find the, right, change in current because I knew what the inductance was. Okay? All right, now a long time after the switch is closed. All right. A long time after the switch is closed, these inductors are going to act like wires. The inductors are just going to act like wires in the circuit. Wires that allow current to flow, happy, happy, happy current flow, right? Since the current will no longer be changing as a function of time, the voltage drop across the inductors will be what? If the current isn't changing, 0. So the voltage drop across any of these inductors is going to be 0 after a long time. Which means the voltage drop across the 40 millihenry inductor is going to be 0. In fact, all of the current from the battery is going to flow through the 40 millihenry inductor after a long time. Because even this other inductor has this, that would end up, it would just all go down here. So this will actually start draining its current. And finally, when it gets all balanced out, I do not want to set up a differential equation for this thing, by the way. Maybe later on you'll have to. But what is going to happen is that all the current's going to flow here. You're going to get 10 amps flowing through here, because the only resistance there is the 10 ohm resistor. That's it. Yes?
So because the inductors do have some internal resistance, it's not a hard 0.
Right, it's not a hard 0, it's a soft 0, yes.
It's an almost 10 amps.
And almost 10 amps, and an almost 0 voltage. Almost, yes. Yeah, when you get the real life situations, yes. But in theory land, that's 0. Okay? And, you know, in terms of that, in terms of the voltage potential drop across that 60 ohm resistor, you know, since we're not going to calculate, you know, soft, you know, there's no place to put soft 0 in master physics. Just put 0. Yeah, there would be a little bit more. Not much. Okay. All right, let's move on to our last chapter. This is going to be exciting. No? Well, the last chapter we're going to cover. I might cover a little bit of chapter 32, but not much. This is our main last chapter that we're going to cover. Okay. And I actually started it last week. I don't really like what the book did, but it's one or the other, doesn't it? Okay, so last time what we did was we talked about the RMS current and the RMS voltage coming out. So in other words, if I have a sine function or a cosine function for my current, so we're going to have the current here, and we're going to say that the current, because we're going to be looking at the current here in this case. The current in this case is some Imax, or let's say that is. Let's see what letter they use. Oh, they just use capital I. I don't like that. So I'm not going to use capital I, because capital I is so I'm going to say that it's equal to some. Should I keep okay, capital I. Times cosine of omega t. Okay? So in other words, when we use our generator, we're going to be generating a particular voltage. That voltage is going to be in the term of a sinusoidal function. So therefore, the current in your circuit is also going to go as a sinusoidal function. In order to analyze this, we're actually going to remove the phase from the current. So in other words, we're going to define our current as being a nice cosine function. You will see eventually that this will throw the voltage off. This will actually throw the voltage off of it. But it's okay for our purposes because that's what we want to do. We want to analyze it. It's simpler to analyze it with a current like this. Okay? So current with no phase in. All right, so first thing we want to look at is a resistor. So I have an oscillator or an AC current generator. To put that in your circuit, it's this with a little wave on it. You put a little wave, that's your AC circuit generator. That generates AC current. The current is coming out of here, and we have a resistor. Ta-da! Resistor R. So now what we want to do is we want to look at how the voltage across that resistor behaves in an AC circuit. So in an AC circuit, we want to see how this behaves. So I have the current coming out of here. Current I, there it is. Now, I don't like this. I'm changing this. That's I not. Okay? I don't like it because of the way that everything does. Okay, so at any point in time, at any exact point in time, the voltage across that resistor will be what? IR. Where I is the current going through the resistor, and R is the resistance of the resistor. Not right. Okay, so here we go. So we have this. So we just plug in this thing. So the voltage across the resistor is equal to I naught times the resistance R cosine omega t. Or to make the weird way that your book does, I guess it's okay. What they say is they say that the VR is equal to, this will be my capital V. Silly. Oh dear. Okay, fine. I'm going to do that because I want a specific notation for this, and I'm just tired of this. So VR naught, which is my maximum voltage here, times the cosine of omega t. Okay? Now what we want to do is I want to figure out how this is behaving in terms of the circuit. Behaving in terms of the circuit itself. Okay? Remember with my I value, okay? I have this letter I right here, and let me see, how do I want to write this? Let me write it let me just write the capital I like this, okay? And from now on, anytime I just use the capital I, okay, in the circuit, okay? No, actually, let me just go ahead and put the RMS voltage. So RMS current in the circuit. And so now what I want to do is I want to figure out how the RMS voltage of this resistor compares to the RMS current in the circuit. To the RMS current in the circuit. Well, if they take the RMS of this cosine function, I have this thing divided by the square root of 2. So I have I naught divided by the square root of 2. So this VR, and this is T. This VR is equal to I naught R divided by square root of 2. Okay? So the V R, there's my maximum VR max divided by square root of 2. There you go. I want no subscript here to be the voltage, the RMS voltage across that resistance. I want no subscript to be the RMS voltage. Okay? Otherwise, then I'm going to have to write RMS all the time, and I don't want it. Okay? Because when I go to measure my voltage across that resistor, I'm measuring an RMS voltage. Okay? So that's where I want to get. But anyway, what I wanted to show you is kind of simple. The RMS voltage across the resistor is equal to, here's the RMS current, multiplied by the resistance itself. Duh. Duh. Okay? There's no surprise there. Yes?
Can you use, instead of VRM, VR naught? Is the same?
Yeah, VR naught over, yeah, let's see, yeah, VR naught. Thank you, VR naught. Yeah, thanks. VR naught divided by here. All right, let me try this with the capacitor and clearing up my notes. I should do this again. All right, so your book goes straight to an inductor. I guess we can go to an inductor. Doesn't matter. Got to go to one or the other. All right, so let's take a look at an inductor now. So now I want to see how a inductor responds to an AC circuit. So here's an AC current, an ideal inductor over here. There it is. I naught cosine t. And remember we have our RMS current, which is I naught over 2. Okay, let's figure this one out. Well, I'm putting this current through an inductor. So the voltage across an inductor is my inductance multiplied by di dt. I want to take a derivative of this. Derivative of that is what? So I get negative sine negative I naught, got a L, got a sine of omega t, and a factor of omega comes out here. So my inductor, so if I take my RMS voltage of the inductor, okay, RMS voltage of the inductor is equal to this factor out here divided by what? The square root of 2. So it's I naught L omega divided by the square root of 2. Which is equal to the RMS current multiplied by L omega. All right, well, let's look at the capacitor. See what happens with it. Now let's put a capacitor over here. Put a current through it. Once again, we have our I equals I naught cosine omega t, RMS I naught over square root of 2. Voltage across capacitor is a function of time. So you go to Q over C. How do I Q out of that thing? If I know Q is a function of time, how do I get the current? Yeah, I take a derivative. So in other words, the current is dq dt. So now if I want to go the other way, what do I need to do? Integrate. Integral of cosine is? Sine. It's positive sine. Integral of cosine is positive. Okay, so integral of cosine is positive sine. So what we have is we have I naught. Now the factor is different now because it's 1 over omega that comes out because I'm integrating, not differentiating. So I need to divide by the omega inside of here. So I naught C omega sine of omega t. My RMS voltage then is equal to I naught over the square root of 2 capacitance multiplied by omega, which is equal to I RMS divided by omega c. Now, when I look specifically at just the RMS voltages that we're looking at here, just the RMS voltages, okay? What are the units of L times omega? What do they have to be? They have to be in ohms, because you've got a current times something equals voltage. So this has to be in ohms. What about this 1 over omega c? What's the units of that? Ohms. So in terms of the RMS voltages, when we're looking specifically at the RMS values, these things act like resistances. And so what we do is we define something called a reactance. So a reactance, for lack of a better word, because I cannot, because it's hard for me to explain, but basically it's the resistance of a circuit element to an alternating current. That's what it is. And notice I'm putting resistance in quotes, because it's not really a resistor. It's a capacitor and an inductor. They're not really resistors, but they kind of act like one when you try to put certain currents in. Now, of course, by the way, if I defined a reactance of a resistor, there really isn't any, but it would just be the resistance itself. Resistor directly translates. Okay? So we have the resistor R. So that's just R. Okay? My reactance of my inductor, how much it resists current, that's equal to omega times L. And the reactance of my capacitor is equal to 1 over omega C. Notice that the inductor and the capacitor, how they react, or their reactance, depends on the frequency of the current that you're trying to put into the circuit. Let's start with the capacitor. Now remember that if the capacitor gets charged up, it will block current. If the capacitor gets charged up, it will block current. So with low frequencies, so I'm going to kind of replace my oscillator with just a rotating battery. Okay, so we can kind of understand it. It's not really rotating, but to kind of understand it, how these relationships are with frequency. So I start with the capacitor. Okay? Okay, so if I've got a low frequency, then the capacitor has plenty of time, charges up, blocks the current. But at very high frequencies, okay, I start to charge it, up, switch the battery, up, switch the other side, up, switch the other side, up, switch, so I keep switching it, and the capacitor just does not have time to charge up because I keep switching back, like this. Okay?
Can you do that again? I don't think you got it.
Sure. Here, in fact, I'll do it over here. So you can all see it like later, okay? So when you've got a capacitor at a very low frequency, the charge gets on the capacitor and blocks the current. What happens? If I change the battery, I got plenty of time to get back over here and block the current again. Plenty of time to get back over here, block the current again. Well, that's the capacitor at low frequency. So low frequency, capacitor is going to have a very high inductance. Okay? Now, let's say I start to charge it up here. I got high. Oh, I switch the battery. I'm going to go back. Up, switch. Up, and then faster. At higher and higher frequencies. Can never get any charge on. Like that.
You think you're trying to do someone a vertical massage?
It's good exercise. Okay? So that's what happens with the capacitor. So very low frequencies, the capacitor has a high reactance. Blocks the current for low frequencies. So the thing about this is that this actually has an adjustable resistance, if you will, for an AC circuit. At low frequencies, it blocks. High frequencies, we'll let it pass. Let's take a look at the inductor. Now remember our inductor. Inductor H change. H change. So here I'm going to go. I have an inductor now. I'm going to do it here so you can also watch me make a total fool of myself on YouTube again. That's what I'm doing here. So I have an inductor. Okay? Now, at very low frequencies, you give the inductor plenty of time to get used to the current that you're trying to push through it. Position it the same way, kind of massage the inductor. Oh, the inductor's nice, it lets it through. No problem. Okay? No problem. So it lets current through at low frequencies. Now if I start doing high frequencies, the inductor is going to keep fighting me. And basically, if I put a high frequency on an inductor, the inductor goes, no! Stop changing the current so much! So at very high frequencies, the inductor has a high reactance. All right, so now let's put them together. Let's put them together. Okay. So what we call a series, and I guess I'll say RLC. Sorry. And this time we're going to work with the AC. So I have an AC current coming out here, and I have a resistor. I have an inductor, and I have a capacitor. Resistor, inductor, capacitor. And I put them all together in the circuit. And so now what I want to find out is I want to take my reactances and I want to calculate a total reactance or total resistance for this whole circuit here. The total resistance. So they're in series, so you just add them up. Well, you can't. You can't add them up. You can't just take these values, because these values, remember, were based on the RMS currents and the RMS voltages. Problem is that this one's maximum voltage doesn't happen at the same time that that one does. And that one doesn't happen at the same time that this one does. They all happen at different times. So the way to add them up, we have to use what's called a phasor diagram. So we use a phasor diagram to add these up by taking into account when the voltages happen. So what we do is we say, okay, here, draw an axis like this, and here's my phasor diagram. What I do is I put the current along the x-axis. I put the current along the x-axis. Now if I were to sum my voltages up, what I would find is that the voltage of my resistor is in phase with the current. The voltage of my resistor is in phase with the current. So when the current is maximum, the voltage across my resistor is maximum. Okay? So the resistance goes right along the axis of the current in, because it's in phase with that current. So here's my voltage across the resistor. In phase with current. Now an inductor, when this is maximum, it's already 0, and then it moves ahead. So the inductor, its voltage is 90 degrees ahead of the current. So the voltage of the inductor is here. Voltage of the inductor is there. And the capacitor is 90 degrees behind it. 90 degrees behind my current is the capacitor. So it's down here. My voltage across the capacitor, 90 degrees. It lags the current by 90 degrees.
Is there a reason why you made it shorter?
I could have made it longer. I could have really made it the same size if I wanted to. There's no particular reason. It's just the convenience of this diagram here. That's the why I did. Okay, so now to get the total RMS voltage that we actually would measure in a circuit like this, you have to add these three things up. Because they're out of phase with each other, you basically take the vector sum of them. These two tend to cancel each other out. So what you have here is you have a this right here, which is the absolute value of VL minus VC. In other words, I took that difference first, and then I add them up. To get the total voltage, RMS voltage in the circuit. I guess V total, or V battery, or V whatever. How do they use? I'll look up later. Okay, V bat. V total. Okay. So what is that V total? What is that V total? Well, the V total calculates a vector sum. It's equal to the square root of the voltage across the resistance squared plus the voltage across the inductor minus the voltage across the capacitor squared. And you also get an angle out of this, known as the phase angle, phi. The tangent of that phase angle phi is equal to VL minus VC divided by the resistance in your circuit, R. If any element in your circuit, whoops, sorry. I'm in voltage land here.
VR?
Yeah, VR. Yeah, I'm in voltage land, yeah. Bear with me just for a couple seconds more. If I took this entire diagram and divided everything by the RMS current, then I could draw the very same diagram using my reactances rather than using the voltages. So my resistance would go along the x-axis, my inductive reactance goes up, positive y, my capacitive reactance is in negative y direction. The total in this circuit is then called the impedance. Impedance. We use the capital letter Z. Z. Okay? I will actually draw that for you on Wednesday, but that's where we're going to start. Okay? Now where we're headed.